Hey guys, in this video we're going to look at the concept of independent events and whether one probability affects another. I guess in the last video we learnt the probability of A given B is the probability of A intersects B over the probability of B. We also learnt that the probability of A given B is equal to the probability of A if they're independent. Because if B doesn't affect A and B are independent. Now you can see from this here, if we know the rule above, if A and B are independent, we can replace that with the probability of A, only if they're independent. And from this, we say if independent. From this, we can see the probability of A times the probability of B is equal to the probability of A intersects B if they're independent. So if this rule holds, you can say A and B are independent. Also, if the probability of A, given that B has occurred, is the probability of A, or the probability of B given that A has occurred is the probability of B, then we also know they're independent. Independence means one thing doesn't affect the other. So if they say it's independent, we can assume this rule. Or if they ask for independence, we can see whether this rule is true. And if it's true, we know they're independent. So if the event A has no effect on B, then two things are independent. So the probability that Monica remembers to do her homework is 0.7. The probability that Patrick remembers to do his is 0.4. If the events are independent, i.e. they have no effect on each other, what's the probability that they'll both do it? Monica and Patrick both doing it, but we just multiply their probabilities. We get 28% or 0.28. What's the probability that Monica will do hers and Patrick won't? So if Monica does hers, it's a 0.7. Patrick not doing his is 0.6. So that's 0.42. Now, if you had something that was dependent, it could be that Patrick and Monica are boyfriend and girlfriend. They would affect each other's outcome on doing homework because they might text each other or they might ring each other and spend heaps of time on the phone. So they wouldn't be independent. But they don't affect each other. Okay. What's the probability that if a ball is drawn 3 times from a jar containing 4 white and 6 black balls, with replacement, a white ball would be drawn exactly once? Now we're putting the ball back in. So if I want to get a white ball exactly once, we know the probability of a white ball each time is the same because we keep replacing the ball, which is 4 out of 10. Which is 2 out of 5. The probability of a black ball is 6 out of 10, which is 3 out of 5. Now this is an example of a discrete random variable because we want to work out the probability that a white ball is drawn exactly once. So if I want the probability of a white once, we could have white, black, black, or we could have black, white, black, or we could have black, black, white. In the first case, white we know is 2/5, black is 3/5, and then 3/5. A black is 3/5, a white is 2/5, a black is 3/5, a black, and then a black, and then a white. Now you can see they're all exactly the same. This is an example of a binomial distribution, which is what we're going to be going through in the next topic. If we multiply the top, we get 2 times 3, which is 6, times 3, which is 18, on 125, and then 18 on 125, and then 18 on 125. When we add them all together, we get 54 on 125. So that's our probability of getting exactly one white ball. Okay, consider the table shown. Does this meet the conditions for a discrete probability? Well, I spoke about in one of the earlier videos. Is the sum of all of the probabilities equal to 1? Well, 0.2 plus 0.3 plus 0.1 plus 0.4 equals 1. So we know that's true. Next are all probabilities. 0 is less than our probability, which is 1. That's also true. So, as the sum of all probabilities equals 1, and all of the probabilities are between 0 and 1, this is a discrete probability distribution. And they're all discrete values. Use the table to find the probability that x is less than or equal to 2. So less than or equal to 2 is this. Which we can see is 0.2 plus 0.3 plus 0.1, which is 0.6. You can also see the probability that x is less than or equal to 2 is 1 minus the probability that x equals 3. 1 minus 0.4, which is 0.6. So we call this using symmetry, because we know all of the probabilities must add to 1. So if we do 1 take away these, we end up with that. Okay, let x be the number of heads showing when a fair coin is tossed 3 times. From the probability distribution of x, show that it adds to 1. Now I've already done this before. We know we've got head, tail. We've got head, tail. We've got head, tail, head, tail, head, tail, head, tail, head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. 3 heads is 1 out of 8. X is the number of heads, so we know that's 1 on 8. 2 heads, 2 heads, 2 heads. Is 3 out of 8. 1 head, 1 head, 1 head. X is equal to 1. Because x is the number of heads, in this case x is equal to 1. That's 3/8. 0 heads is 3 tails, so we get 1 on 8. If we sum them all, we get 1 on 8 plus 3 on 8 plus 3 on 8 plus 1 on 8, which is 1. Find the probability that 1 or more heads shows. So the probability that x is greater than or equal to 1 We can also say that's 1 minus the probability that x is 0, which is 1 minus an eighth, which is 7/8. And you can see if you added them together, you would get 7/8. The probability that more than one head shows, well, that's the probability that x equals 2 plus the probability that x equals 3, which is 3/8 plus 1/8, which is 4/8, which is a half. You can also see that that's 1 minus the probability that x equals 0 minus the probability that x equals 1, which is 1 minus 3/8, 1/8, and 3/8, which is 4/8 or 1/2. Okay. An experiment consists of tossing an unbiased coin and tossing it again if and only if the first toss yielded a head, and then tossing it again if and only if the second toss yielded a head. So, first toss, we can get a head and a tail. We only toss it again, second toss, if we got a head, and then we only toss it again if we got a head again. We know when it's unbiased, we've got a half and a half, a half and a half, a half and a half. Now, if I said to you, if x denotes the total number of heads, here we get 0, x equals 0, and that probability is 1/2. Here we get 1 head and 1 tail, so in this case x is equal to 1. We've got a half times a half, which is a quarter. Next, we've got a head, and a tail. So x is equal to 2, and that's a half times a half times a half, which is an eighth. And then last, we've got head. X is equal to 3, and that's a half times a half times a half. So 0 heads is a half. 1 head is a quarter, 2 heads is an eighth, 3 heads is an eighth. We can check and make sure they all add up to 1. So a half plus a quarter plus an eighth, which is 4/8 plus 2/8 plus 1/8 plus 1/8. Which is 8/8, which is 1. So we know it's a probability distribution. Okay, the random variable x represents the number of chocolate chips in a certain brand of biscuit, and it's known to have the following probability distribution. So the probability of getting 2 chocolate chips is 1%, 3 is 25, 4 is 40, 5 is 30, etc., etc. Find the probability of getting more than or equal to 4 chocolate chips. So we know it's 0.4 plus 0.3 plus 0.02 plus 0.02, which is 0.74. So there's a 74% chance. Excuse me. Or we could have done 1 minus those two. The probability that x is greater than or equal to 4, given that x is greater than 2. So in this case here, we want to find where they intersect. Because our rule is x is greater than or equal to 4 intersects x is greater than 2 over the probability that x is greater than 2. So in this case, what I would do is draw a number line. 2, 3, 4. Greater than 2 is an open circle. Greater than or equal to 4. Where do they intersect? For x is greater than or equal to 4. Greater than 2, we can say, is the probability that x is greater than or equal to 3. Greater than 4, we know, is 0.74. from here. Greater than 3, we just add on 0.25, so we get 0.99. So we get 74 over 99. And the next one, the probability that x is less than 5, given that it's less than or greater than 2. Number line, 5, open circle to the left, 2, open circle to the right. Where do they intersect? Between 3 and 4. So we can say the probability that 3 is less than or equal to x, which is less than or equal to 4, over x is greater than 2, we know x is greater than or equal to 3. So between 3 and 4 is, add them together, 0.65. Greater than 3, we know is 0.99, because we just did that, which is 65 over 99. So that's our probability of getting less than 5 chocolate chips, given that we had at least 2 chocolate chips. So that's looking at discrete random variables and also independent events.